Hello, my name is John Paul Metz. I currently work for General Electric as a software and controls product service engineer. Our team helps service, maintain, repair, and upgrade heavy-duty gas turbines located throughout the entire world. This presentation is about a specific project I worked on where I utilized UML, or Unified Modeling Language, to design a gas turbine fuel leak protection system for these heavy-duty gas turbines. This presentation, I will first give an introduction of the problem statement, then I'll give a brief background on gas turbines and the UML design process. Next, I will discuss the functional requirements, how we got them, and how we utilize them with the UML design process. Then I'll show the UML diagram that we came up with and go into detail about one of the specific use cases and how we fully addressed it to understand it. Then I will give brief discussion on the final product that we developed, how we tested it, maintained, and maintained it. And we'll finish with a conclusion. Heavy-duty gas turbines, which I have presented here on the bottom left, are basically like airplane engines, except scaled up a couple of times to about the size of a school bus. These are major components in the power generation and distribution system throughout the world. Many gas turbines operate with natural gas, some with liquid fuel, and they use complex and robust gas fuel systems to ensure the safe filtering and transportation of the fuel to the proper areas of the turbine. Because natural gas operates at very high pressures, these systems have a tendency to leak out of broken seals, out of loose joints, and other areas where slight pressure differentials present themselves. Because these leaks can be present but actually relatively undetectable to the human senses, power plants and other gas turbine operators are mandated by law to install, maintain, and use various fuel leak detection systems. They're relatively common, but some customers request a higher degree of safety and thus a higher degree of sensitivity and robustness of their gas fuel system. And this project is one of those requests to develop a more robust, more detailed, and reliable gas fuel leak safety system. To do this, we utilized UML, or Unified Modeling Language. The primary purpose for these gas fuel leak systems is safety. You can see here on the bottom right is a fire that actually happened at a power plant. This wasn't due to gas fuel leak. This is just an image that shows the impact that any fire can have at a power plant. Now, next to safety, the next most important thing to the customer is operational efficiency and cost. Leaking fuel means leaking money. Fuel is very expensive. So not only is the actual operational efficiency of the power plant decreasing, but you're actually wasting money by letting fuel leak out. So some more detail on a gas turbine. Gas turbines, natural gas-fired gas turbines, create about 35% of the United States electricity. General Electric is a lead gas turbine manufacturer in the United States and the world. In fact, about 1/3 of the world's electricity is produced by various General Electric machinery. A gas turbine has 5 major systems. I'll direct you to the images on the right. First on the top is a diagram of a Kawasaki single shaft gas turbine. And this just goes to show, I pulled a Kawasaki image, that gas turbines are a very well understood and mass-produced piece of machinery. And they have a couple of standard systems, not specific to General Electric. First is the compressor. The compressor's one job is to take as much air as possible, compress it into a very, very small space, and then deliver that compressed air to the combustor just downstream. The combustor is the next major system, and its job is to receive fuel, either liquid fuel or natural gas, and burn all of that highly compressed air to increase the energy contained in the air by increasing the temperature and the pressure even more, and then sending all of that hot air to the power turbine. The power turbine is the third major system within the interior of the gas turbine, and its goal is to spin and to extract as much energy from that air as possible to create torque. That torque is then connected to, or transferred through the rotor to a generator and produces your electricity. Now, in addition to those three major systems, interior of the gas turbine, there are many, many systems which are all considered auxiliary systems. That includes air control, fuel control, oil control. Those are all part of the auxiliary systems. And then finally is the software. Controls is, in most gas turbine manufacturing and maintenance companies, controls is considered its entirely own system. To summarize a gas turbine, a common phrase is suck, squeeze, bang, blow. We want to suck in air, squeeze it, pressurize it. We want to explode it, increase the temperature, and then blow it out through the turbine. UML, or Unified Modeling Language, is a design tool that we used to understand these auxiliary systems of the gas turbines in order to improve our knowledge and create an even better gas fuel leak system. Some background on the UML. There's four major components. Here on the right is an example of a use case UML diagram. The first component to point out are the actors. Actors in a UML use case diagram are anyone or anything that acts, is impacted by, or in some way related to various systems and actions that we call use cases that exist within the system boundary. So this black line is the system boundary. In this example, it's a banking application on a cell phone. The actors are the customer and the bank. The use cases are various things that the customer or the bank can do within this banking application, like log in, check balance, transfer funds, etc., etc. And then the last component of a UML use case diagram are the various relationships that exist between the use cases and between the actors and the use cases. So now that I've given you a brief introduction of the problem statement and some background, I want to jump into the details of this project. First are the functional requirements. These functional requirements, located here in the center, became the use cases in our UML diagram. Very simply, this software program that we developed for this gas fuel leak safety system had to primarily detect a leak and identify the leak location, functional requirement 3 and 4. But to do that, we needed to redefine our signals, determine signal health on all of the equipment that we were utilizing. And then once we had detected and identified the leak and the leak location, we wanted to alert the power plant operators and initiate turbine protection. You can see on the outside are all of our stakeholders: plant operator, power purchasers, General Electric company, investors. There are many different components that came into developing these functional requirements. Once we had these, we actually built our UML diagram. Here, again, I want to point out we have 5 different types of actors. We have sensors, which are not people, but they're actually equipment. There's all other instrumentation. There's valves, plant operator, and the actual gas turbine. So note that of the actors, there's only actually one human, and that is the plant operator. Now, within the system boundary that we labeled gas fuel leak safety software are 1, 2, 3, 4, 5, 6, 7, 8 use cases. And I'll flip back. The functional requirements became the use cases. This was crucial to the UML diagram and the development of this project. Within the UML diagram, you can see the different relationships. The most apparent relationships here are the include relationships. Include relationships in the UML diagram are use cases that will happen immediately following the original use case. So in this example, as soon as a leak is detected, we can follow our include relationship line. 2 things will happen. First, an alarm will sound, which the plant operator will notice. And second, the turbine initiation protection will happen, and that the gas turbine will be affected by that. Now, within these different use cases, there are a lot of other scenarios, situations that could affect them. So to understand some of the more complicated use cases, we fully dressed the identify leak location because this was the most complicated use case in the system. What I have here is the diagram, the table that we created to detail all of the different parts of a fully dressed use case. A fully dressed use case is a very standard table used by UML use case design methods. First, you have the name, actor, trigger, various conditions. Excuse me. Various conditions that must predate and postdate the various use case. Our primary success scenario. This success scenario is basically what we want to happen for the system to operate perfectly. And then there are alternate flows, is what happens if the system doesn't operate perfectly. Now, the meat of this project exists in this success scenario. This is the goal. This is the objective. If this success scenario is fulfilled, then our problem statement will be complete with a proper functioning solution. Fully dressed use cases are incredibly important and useful in UML because they simplify complex issues, they clarify ambiguous scenarios, they add structure, and supply very specific details and steps of what a specific design is looking for or is intending to accomplish. So now that I've given the UML diagram with some details of the fully dressed use case, I want to point us to the actual final product. On the right, I have a flowchart that we used to show the software. I couldn't actually take pictures of the software because it is confidential information. Now the product consists of two parts. First is the hardware. There's extraction points, there's valves, there's piping, there's sensors, thermocouple pressure sensors, PIR or photoelectric infrared sensors that you could say smell or see unburned hydrocarbons. So these pipes, these extraction points are located throughout the gas turbine and throughout the gas turbine enclosure. And if any leak happens, these extraction points are located at low pressure areas. So that fuel will travel to these low pressures, and the leak will be sucked up in through the extraction port, sent through a series of valves, and be read by these sensors as unburned hydrocarbons. When these sensors look labeled on the right side here as 1A, 2A, 1B, 2B, etc. When these sensors detect the unburned hydrocarbons, they will then initiate the valves through a series of switches. Pictured on the bottom left shows one of these valves, and will hopefully, if everything goes properly, identify exactly where the leak is coming from. Now, it's imperative to find out where the leak is coming from because this leak could be happening anywhere in the gas fuel system, and it can take days and cost the company millions of dollars to go identify exactly where this leak is or replace the entire system entirely. But if we know exactly where the leak is coming from because we know exactly which extraction port the leak was first detected in, then we can save the customer a lot of time and money. This was an example of some of the testing that we had to perform on the software before we actually installed it. On the left here is just a very brief table that shows the valves, the different manifold and sensors that were used and which ones were failed at the time. Now on the bottom right is data that we actually extracted. You can see our sensors increasing and decreasing as we switch the valves and pass the samples from one sensor to another sensor in an effort to identify exactly where this leak is coming from. Ultimately, UML was an excellent tool for designing the gas fuel leak safety system. The system was installed and is currently monitoring multiple units. We haven't had any issues with it except for one, and that was one shortcoming of the UML that we wish we had incorporated earlier, which was environmental impacts that affect the system. One of the units that we're monitoring is located next to a solid waste treatment facility. Now, unfortunately, the solid waste treatment facility releases a lot of hydrocarbons into the air. Not only does the plant smell like sewage, but these unburned hydrocarbons were originally being picked up by our sensors. And because we didn't include environmental impacts in our UML fully dressed use case, this caused some issues. Now, luckily, we were able to identify the issues quickly and go back and fix it. But this was one bit of lessons learned from utilizing UML. Finally, for future work, we would like to continue to modify our software to accommodate some of the extra sensors that we installed, knowing that we would readdress and redesign this system in the future. We specifically want to take lessons learned from various relationships between fuel leak and thermocouples that we have from our install base and incorporate that into our software. Thank you very much. I hope you enjoyed.